Hello everyone, I'm Wenlong from UC Berkeley. Today I'm very happy to talk about my recent work on linear stochastic approximation, fine-grained Polyak-Ruppert and Non-asymptotic concentration. This is a joint work with Chris Junchi, Martin Wainwright, Peter Bartlett, and Michael Jordan. So the problem under our consideration is the simple problem of solving a linear equation. And we consider it under the stochastic approximation setup, where you receive IID sequence of uncorrelated and unbiased observations. In this setting, the classical result by Polyak, Judiski, and Ruppert shows that you can simply take the average of the LSA procedure. And under the condition that the population level matrix A bar is Hurwitz, which means that the real parts in its eigenvalues are strictly positive, and you can take a decreasing step size sequence, and you can have pretty good asymptotic guarantees for the averaged estimator. Actually, this Gaussian limit is locally asymptotically minimax. So given this classical asymptotic results, what is not known yet? There are three questions that motivate our work. The first question is, what is the role of step size? For the asymptotic result, the effect of step size is not fully captured. And it is known that for linear stochastic approximation, you can take a much larger constant step size sequence. And the step size also play an important role in the trade-off between the convergence speed and asymptotic behavior of the estimator. The second question is the non-asymptotic guarantees. Ideally, we want the non-asymptotic properties of our estimator to be as close as the asymptotic Gaussian limit as possible. And it is worth noticing that in many applications, we need more precise bound beyond the L2 norm. The third question is, what is the necessary and sufficient condition for the Polyak-Ruppert procedure to work? In particular, the Hurwitz condition is needed in the asymptotic result. But what if this condition is violated? These three questions motivate our work. Let's first look at two motivating examples. The first example is from stochastic optimization. You are trying to solve this linear regression problem, and of course you can use SGD to solve that. And in such case, the population level matrix A is just the covariance of the design vector, and this becomes the simplest form of linear stochastic approximation. But maybe you can use a more advanced algorithm for that, which is Polyak's heavy ball method. And by using a dimensional lifting trick and introducing the vector v, it becomes a jointly LSA problem. And in such case, the population level matrix is asymmetric, and it has more complicated eigenvalue structure. It is interesting to see the effect of eigenstructure on the acceleration phenomenon. Our second example comes from reinforcement learning theory. Consider a Markov reward process on a finite state space. And we get observations from a generative model where the observations are IID, and for each round, you have a random reward and random state transition at each state. And it is natural to ask the question of value function estimation. And the value function is defined by the solution to a Bellman equation, which is a linear equation. Actually, in such case, the classical TD0 algorithm is essentially the linear stochastic approximation in this setting. And it also has more complicated extensions, such as the undiscounted problem and the problem of the linear function approximation. Along this line of research, there are a lot of existing works. As I just mentioned, there's the classical asymptotic guarantees. And more recently, there are also non-asymptotic guarantees in stochastic optimization setting. It is worth noticing that we can obtain a MSE bound whose leading term is the same as the trace of the asymptotic covariance, which matches the behavior of the limiting Gaussian distribution. And beyond the stochastic optimization setting, there's a recent result for general constant step size RSA, and they show some MSE bound for the averaged iterate. But the MSE bound can be loose in terms of the dependency on the minimum real part of eigenvalues. There are also recent work on instance optimal error infinity bound for value function estimation, as we will discuss later as an application of our general result. So let's first look at some basic properties of the iterates. Under the condition that the matrix A is Hurwitz and some second moment bounds, we can easily show a stability guarantee. If the step size is upper bounded by this constant, we can show the existence and uniqueness of the stationary distribution, and actually the iterate converges pretty fast to the stationary distribution. Using these basic properties, we can show an asymptotic guarantee for the averaged iterate. As shown in this theorem, the limiting distribution is a Gaussian distribution, but the covariance is a sum of two terms. One of the terms is the classical A bar inverse sigma star A bar inverse transpose term, and the other term depends on a matrix lambda eta star, which is the solution to a generalized Lyapunov equation. This matrix is actually the stationary covariance of the iterate themselves. From this equation, we can see some properties of this matrix lambda eta star. For example, if you take small step size, this matrix is upper bounded of order eta. And on the other hand, the solution lambda eta star depends inverse proportionally to the Hurwitz parameter, which is the minimum real part of eigenvalues of the A bar. This property is important for later applications. So let's take a closer look at the momentum SDD examples through the lens of our general asymptotic result. By lifting the dimension, effectively you make this matrix A into this matrix A tilde, which is a symmetric matrix, and also you change the noise structure. And as through some simple calculation, we can see that the optimal covariance term doesn't change, but there are some acceleration effect from the mixing time and the bound on the correction term. Actually, both of the terms can be improved by a square root order. Both terms actually depend on the k quantity, which is the minimum real part of eigenvalues of this matrix A tilde. And by choosing the momentum parameter alpha optimally, we can show upper bound on. We can show that you can improve this minimum real part to square root of lambda mean of A. This improvement is significant when the matrix A is yield conditioned. Now we already have the asymptotic guarantees, and it is natural to ask what is the non-asymptotic counterpart of the result. Recall that in classical Lacan theory, the Gaussian limit is not only optimal and in terms of having the smallest variance, but it is actually optimal under any ball-shaped loss function. This is a very strong guarantee. And ideally, we want the RSA estimate to satisfy the same property in a non-asymptotic sense. And in many real-world applications, the MSE bound is also not sufficient. For example, you may consider error infinity norm, which is a gauge norm defined by a cube, and you measure the width of the Gaussian distribution only along a few fixed directions instead of treating all the directions uniformly. And in such case, you can have a much better dimension dependency. And if you only have a MSE bound or L2 norm bound, this information is lost and you cannot recover this kind of nice bound. So ideally, we want the estimator to have a behavior that matches the behavior of Gaussian limit vector at any fixed direction. And through some empirical process argument, we can show non-asymptotic guarantees under any gauge norm. And our non-asymptotic results shows that this can be true. Actually, we show that under some tail assumption and a slightly stronger requirement on the step size, at any fixed direction, we can show an upper bound which matches the behavior of a limiting Gaussian random variable up to constant factor and additional high order term delta t, which goes to 0 as t goes to infinity. And we can also see the trade-off between the convergence and asymptotics from this bound. There's in addition to the optimal Gaussian limit term, there are like two terms that depend on the step size. The first term is coming from the asymptotic, the correction term in the asymptotic covariance, and this term scales linearly with the step size. And on the other hand, the delta t term has an inverse, it's inverse proportional to the square root of step size. And if you trade off the two terms, the optimal choice of the step size is actually t to the minus 1/3. As an application of our general result, we consider the TD learning example we just discussed before. In the discounted problem, both the contraction bound and the noise bound are in the iron infinity norm. So we need to do some slight modification on the arguments. But following essentially the same line of argument, we can show the following non-asymptotic guarantees. It's worth noticing that the leading term in this iron infinity norm bound almost matches the behavior of the Gaussian limit. And moreover, the additional terms only has the logarithmic dependency on the dimension. So the entire bound also has logarithmic dependency on the dimension. Now we have the asymptotic and non-asymptotic results, both in the Hurwitz case. And in many applications, the underlying population level matrix A is not Hurwitz. Let's look at this complex plane. To the right of this yellow vertical line is a Hurwitz case. The Hurwitz parameter is lower bounded by lambda, and it is safe to apply the asymptotic and non-asymptotic results. And in the gray region, where the eigenvalue can have negative real parts, the iterates are exponentially blowing up, and there's no hope at all. But between the two cases, there is the interesting case, which is a critical case. In many applications, the minimum real parts of eigenvalues can be exactly 0, or even if it's non-zero, it can be extremely small to be so that it's not useful. And this can happen, for example, in average cost TD learning or TD with linear functional approximation. And this also happens with stochastic minimax optimization. And an important thing to note in such setting is that LSA iterate itself does not converge at all. However, even in this extremal case, we show some additional benefit of averaging. In particular, assuming that the population level matrix is diagonalizable with non-negative real parts in the diagonal elements, we can show in the eigenvalues, we can show non-asymptotic MSE bound that achieves the optimal of order 1 over t rate, even if there's no contraction in the iteration at all. The downside of this theorem is that it has a suboptimal problem-dependent constant, and the contribution from initial conditions is not being exponentially forgotten. So given the current work, there are a lot of future directions to extend. First, it is not clear how to use an online procedure to achieve the optimal problem-dependent constant in the critical case, as I just discussed. And there are also a problem of effects on the how to characterize precisely the effect of the momentum on the asymptotic covariance. And in the TD learning example, although we have only logarithmic dimension dependency, but the dependency on the discount factor is not optimal. And in an extremal case, if the discount factor is 1, it comes to the average cost TD problem. And it's also interesting to see the instance optimal iron infinity bound in such setting. And there are also possible extensions by linearization to the nonlinear setting. Okay, thank you.